Hey students, this is your Professor Omelianchuk, and today I want to talk about soundness and completeness, or why every derivation is valid and every valid argument is derivable, right? All right, so here's the deal. Why are we kind of revisiting derivations, right? We're actually not, right? We're not going to go over any more derivations or do any more derivations, right? The reason why we are bringing this back, though, is because we kind of left behind now the logical languages that are purely truth functional, right? So the CL, CL star, TFL, and the digital circuitry, those are truth functional languages that we're going to leave behind. And now we want to get into kind of a meta-analysis of our languages and talk about what we want, like a derivation system, what kind of properties we want it to have in a language like TFL. Okay, and why it's important. And so it also bridges into the next logical language, the very last one we look at, which is called first order predicate logic. And that's an analysis of not only truth functional terms, but also like terms like all, none, some, every, those kinds of words. Right, we're going to be taking a look at that just very briefly. And soundness and completeness kind of bridges that us into that type of thinking. Okay, so before I get into any of that, though, I did want to review something that was important to me to talk about, and how to draw circuits in a simpler way. Now, in the last lecture, I taught you a very complicated way of drawing the circuits. And the reason I did that, I mean, it wasn't to frustrate you, but it was to kind of give you an understanding of the theoretical relationship between the normal form sentence and the digital circuit. So what we ended up doing when we were drawing it is that we zeroed in on the main connective and identified that as the output gate. And then we kind of worked our way from the outside in. Right? And I showed you how that all mapped on to each other. If you were trying to follow that and got super lost, don't feel bad, all right? That's actually not a very practical way to draw things. Here's the practical way of drawing things, where you kind of work from the inside out, all right? So let me give you an example, all right? So here's that problem we were kind of looking at. It's a practice problem that we looked at the very end of the last lecture. And you had like 4 rows here that output a 1, and you can capture them. And so in this case, you have A and B and C. And so what you can do is actually halt the analysis right here. You don't have to make one big, long, normal form sentence first. You can actually start drawing. Right? And so what you'll do is you'll draw a piece of the circuit. It's just a piece of the circuit. It's not the whole thing. But notice that this drawing represents the normal form sentence. So what you have as your output gate, as it were, it's not the main connective of the normal form sentence, but it is the main connective of this particular piece of the normal form sentence. Okay, so here's the AND gate, which goes directly into C, and then it's connected up to another AND gate, which goes directly into A and B. Right, so that's going to be a piece of it. That's going to be one, at least a 1/4 of the circuit that we'll need. Right. Then we go to the second row, and that one says A and B and not C. And you can stop that normal form sentence right there and start drawing what that looks like. Right. So what you'll do, right, is you'll draw an AND gate to represent this AND connective here. And that hooks up to another AND gate that goes directly into A and B. But notice now that C is negated. Okay, and so that's why that, so that's a little bit different from the last one, right? But that's part of the analysis. So that's the second piece, right? The third piece is like so. So here you have not A and B and C, and you'll just draw up the circuit like so. So here you have your AND gate going directly into C, and then it goes into another AND gate, which hooks up directly to B, and then A is negated. Okay, so that's the third part of it. And then the last part of it is this one. You have not A and not B and C. And so what you have here is you have your AND gate that hooks up directly to C. And then you have the AND gate that goes, that's negated, right? So A is negated, B is negated. And so there you have, right, a nice little circuit, right? And so you have all the pieces now that you can put together. And so what you can do is you can actually take all 4 of those normal form pieces and stick them into one big long disjunctive normal form sentence. And here it is, right? Now it's all well formed, everything's kind of paired up and neat. Here's the main connective, okay? And then here's the other two disjunctions, right? We connect things to. So there's 4 of the conjunctions here that are all hooked up with disjunctions now. But here's the thing, here's what's easy about this, right, is that you can kind of just, right, start hooking things up, right? So there's the first piece, there's the first one you drew, right? And it's hooked up to an OR gate. You can kind of see, right, it goes right into that OR right there. That's that OR right there. And then it's the other piece of the OR gate, it hooks up to the second one that you drew. Okay, so there's the second one. Okay, and then if you move over to the other side of this the disjunction, right, here's the other OR gate, you hook that up, okay, and that it's hooked up to the third one that you drew, okay? And then the last one you drew is hooked up there, and so those are the 2 OR gates, those are those 2 ORs right there, and then you hook those 2 up to the main connective OR, and then you're done. Okay, now there is a spaghetti junction here about how do you hook everything up to the same node. And you know what's nice for me is that I had a nice little program. I finally found one that allowed me to kind of do this in a nice efficient way. I don't care about that. If it's spider webs to just a bunch of different inputs over here, I don't really care. As long as you label them correctly, I'm okay with that, because you could theoretically just draw them into one place. I don't really care about that. What I want you to do is capture the size and the depth of these things. All right? Okay, so that is the circuitry portion of this. Let's get back into now, just derivations and what's the deal with them and how do they relate to logical languages like TFL. You know, there's a system of derivation, and then there's a semantics of TFL, right? Let's use this TFL as an example here, and just kind of think about them, okay? Now, if you were to remember how derivations work, right, they allowed us to move from one assertion to another in a stepwise fashion in a truth-preserving way. But what we were doing is that we were following rules about how to correctly arrange the symbols of TFL. And we didn't really need to know the meaning of them, right? We could have been just a dumb computer and followed the rules that were programmed into our memory, and we could have figured out the problems, okay? Although, since being human beings that we are, we have a mind that connects with reality somehow. It's really kind of amazing, and knowing the meaning of these things really does help, okay? Anyway, like I said, derivations are syntactic in nature, right? And I distinguish derivations from truth tables, which define the semantics of our language, right? Those are semantic in nature because they're filled with T's and F's, and they're very much, the analysis, truth table analysis is very much dependent on meaning. All right, so, different derivations, of course, can have the same meaning, right? When we're interpreting derivations, right, they can say the same thing. They can be logically equivalent, that is. So, for example, here's a derivation. Okay, it's got 6 lines, right? And it says the exact same thing as this derivation. Notice that line 6 says the exact same thing in line 7. The only thing that's a little different about this one is that we did an extra step, right? We eliminated we eliminated the conjunction on line 2 here. Okay, and we just didn't have to do that. So like this one's like a little more efficient, right? We got to the same result using less steps. Okay, but they have the same meaning, right? However, there's a different arrangement because there's an extra line. Okay, so that's semantically the same, syntactically different. Okay, all right. Now, what I would like to do is this is all kind of building into a theme here. All right, so you're probably going to be wondering, oh, why are we going over this? All right, just bear with me. Here's another thing you're going to be wondering: why are we going over this? Like, why? Here's the rule of conditional elimination. Right, there's a truth table that justifies the rule of inference such that if you have P arrow Q on a line, and if you have P on a line, then you can write Q on a line, because the truth table says, if these two are true, then this one's got to be true. So that's a valid rule of inference, all right? Okay, and you're like, yeah, you've already been over this. Why are you going over this again? Okay, this is all kind of review, right? But what if I didn't give you that rule? What if I was a cruel logic teacher and I didn't give you that rule? Instead, I gave you this rule. Now, hopefully you can see the difference, all right? This one is says if you have P arrow Q on a line, then if you have Q on a line, then you can write P. Right, and that's kind of a weird inference, right? If you know, it doesn't. If you think about it, kind of from an English example, you know, if it's raining outside, then it's wet outside. It's wet outside, therefore it's raining. Well, that doesn't necessarily follow, right? People could have put, you know, they could have taken a fire hose and sprayed, the streets, or somebody's sprinklers, you know, could have been all over the place, right? A water main must have busted, you know, stuff like that. Okay, you know, you might think that something's going on here, right? But suppose I gave you that rule, and then suppose that you took that rule and you derived, okay, I want to derive FA, and I got FA arrow GA on a line and GA, and then you used arrow elimination, right? And you derive FA. Now you would be following a rule, right? You wouldn't be doing anything wrong insofar as the rules of syntax goes. But as far as the rules of semantics goes, you would be going from truths to a falsehood, right? And there's a truth table that can prove that, right? You have here, you know, it's possible for your P, which in this case is going to be FA here, to be false, and you know, your Q here and your arrow to be true. That's what line 3 there is representing. Now, if this happened, right, if I gave you that rule, you would be working with a derivation system that is unsound. Okay, it is an unsound derivation system, right? So what I want you to notice here is that there's a disconnect between our derivation system and the truth tables that specify truth in our language. Right? And when there's that disconnect, that makes James Van Der Beek sad. Okay, we don't want that, right? Okay, so that's the unsound scenario. Let's also imagine this. Here's the rule of conditional introduction, right? And what if I didn't give you this? What if we just said, you know what, you just don't get that rule at all. Okay, you don't get that rule at all. That's just not even available to you. Now you might be kind of happy about that because that's just one less rule that requires you to make subderivations. But then suppose I was a cruel logic teacher, right? And I said, okay, you have to derive this problem. You have to derive FA arrow GA from the premise GA. And you would probably be like, Professor, oh, I don't know what you're talking about. Why? How would I even do that? I don't have a rule that allows me to do that. And the problem here is that you lack a rule that can move you from a truth to a truth, right? And there's a truth table that can demonstrate that. So here's a truth table, right? That, you know, here we have P and Q. Okay, now you can move from Q, right? You know, this is the truth that you can move from the truth of Q to the truth of the P arrow Q. Okay, so whenever Q is true, the arrow formula is true as well. And that, you know, you should be able to do that. You should have a rule that allows you to capture that semantic fact in our language. But you don't. You don't have a rule that allows you to do that. And that makes your derivation system incomplete. Incomplete. That's the incomplete scenario. All right? So let's talk about these two properties, soundness and completeness, okay? These examples, as silly as they are meant to show two ways in which syntax, as specified by the rules of the derivation system, and the semantics, as specified by the truth conditions in your truth tables, could cause trouble for us. Right? Some derivations may not represent valid arguments, as defined by truth in a language. So recall the unsound scenario, where I gave you the screwed up version of arrow elimination. Okay, that's a big semantic problem there, right? So soundness, right, has to do with kind of the semantic problem, right? And then there are some valid arguments that may not be derivable. Okay, so your system of derivation just doesn't have enough rules to push the symbols around to capture valid arguments. Right, that's the incomplete scenario. So remember, the incomplete scenario is the one in which I just don't even give you the rule of arrow introduction. That's a syntactic problem. Right now, these two problems, They can show up in any formal language that contains both truth conditions that are specified by something like a truth table analysis, that's your semantics, and a system of derivation, right, which is going to involve rules of syntax where you can kind of push things around. So the two properties that we want our language to have is this. We want our language to have the property of soundness, which means that that every derivation in the language represents a valid argument. Let's just kind of think about that again. Every derivation we do in the language that we're working with will represent a valid argument. Okay, that's what we want the derivation system to do. Completeness is different. Okay, a language is complete if and only if there's a derivation of every valid argument. So think of all the valid arguments that we could come up with. We want to be able to represent them with a derivation. Okay, that's what completeness means. So you should understand these, right? You should memorize these. These are important to understand. Okay. Okay, so a little illustration of this that comes from the area of moral philosophy, which is an area I work in. Sometimes you hear this said, and this is a Facebook meme, right? I sometimes see this. Now, I'm a philosopher, so I see these memes. I don't know if you have, and I don't even know if you're on Facebook. That's something that older people are on, like me. But sometimes you'll hear people say, you just can't go from an is statement to an ought statement. All right, and so what on earth does this mean, right? You can't make a normative claim from a descriptive claim. That's one way of kind of talking about this. So if you're not really familiar with this, just kind of track with me a little bit here. The idea is that moral facts are so much different from like natural descriptive scientific facts that you can't just derive a moral fact from a scientific fact. Okay, so sometimes this gets asserted, and you'll only hear a philosopher say this, right? Suppose you're the person who's claiming that you can't get an ought from an is thinks this, that you can't move from the observation that the baby is drowning to a moral claim that you ought to help the baby. Okay, and what the problem is here is a move from a truth to a falsehood. And suppose this philosopher who's saying this sort of thing thinks there's just no moral truths at all. Like those just don't exist, in a universe that's only made up of physical particles. I mean, come on. You get down to the fundamental nitty-gritty stuff of reality. There's just no, truth. There's no moral particle, right? So anyway, what this is illustrating is that the moral logic that we're using is unsound because we're making an inference that is taking us from a truth to a falsehood. You also might analyze the you can't get an ought statement from an is statement in this way. Right? You could take it this way. It could mean that the move from an observation that the baby is drowning, all right, to a moral statement that you ought to help a baby is a move from a truth to a truth. All right, so there is a moral fact here. You ought to help the baby, and I hope that you all agree with this, right? But the move is unreliable. All right, because while there are moral truths, there is no valid rule of inference that allows us to move from an observational claim to a moral one. Okay, so there's just no rule that allows this. And so what happens there, right, our moral logic then is incomplete, right? So the reason I'm bringing up this kind of wacky case from philosophy, isn't to kind of make any kind of controversial claims about babies or morality or anything like that, but to give you a sense of how these things come up, right? In one case, you're thinking, we're moving from a truth to a falsehood, so there's something unsound happen. In the other case, we're moving from a truth to a truth, all right, but the move is not something that we have available to us. The rule just doesn't exist. We don't understand how we can make that move in a principled way, and so it's incomplete, right? The moral logic is incomplete. All right, so the point of all this, and also a little tip, is that soundness has to do with never moving from a truth to a falsehood. And completeness has to do with being able to derive every truth. Right, so a tip for your memory here, I like this, as I learned this from a colleague of mine. He said, you know, soundness has a D in it, and that D has to be associated with derivations. Right, the derivations, right, it's the subject of our sentence here. What are we talking about? Well, they all represent a valid argument. All right, they all represent a valid argument. So soundness has to do with representing validity. Right, completeness, on the other hand, has a T in it. All right, it has a T in it, and that's associated with valid arguments as specified by our truth tables. Right, our truth in a language. And all the things that we can come up with in our truth in a language analysis, our truth tables, all of those can be derived. All of those can be represented with a derivation. So the subject of the sentence then are the truth tables, right? The valid arguments that are captured in the truth tables. Those can be derived, right? So that's a way of kind of distinguishing these two. Right, and there's some other memorable slogans. You can get this out of the book. You can say that soundness is that every derivation just is a valid argument, and every valid argument has a derivation. That's what completeness means. Completeness is every valid argument has a derivation. Right, that's a nice simple way of understanding this as well. So for TFL, right, throughout this class, what we've done is we have assumed that our derivation system is sound and complete. Right? I didn't give you any trick questions. I didn't ask you to derive any invalid arguments. I didn't give you any crappy rules. And I gave you all the rules you needed to get the job done. Right? And the textbook you're at this point also assumes this. It doesn't prove that it's the system is sound and complete. Right? You can prove it. The proof for soundness is really simple. You just can use your truth tables to show that every rule of inference is valid. Right, so you just use the truth tables, you put the inputs on one side, you put the output on the other side. You're never going to go from truths to falsehoods. All right. Completeness is much harder, and for that you'll have to take an advanced class, and that's not something I can teach you. This is where the limits of my knowledge on how to do this runs out. I did witness the proof for completeness in my advanced logic class, as taught by the author of this textbook at the University of South Carolina, Michael Dixon. He's a really nice guy. You could actually probably find him on the internet and email him and ask for some pointers. He's super helpful. When we learned this, he brought us over to his house, and we made homemade pizzas and cooked them in his really nice kitchen, and he went over the proof for completeness on a big piece of paper, which I didn't fully understand. So anyway, I encourage you, if you're really interested in this stuff, you can check it out. All right? Okay, things to note. You can have soundness without completeness. Yes. Yes, you can. Okay, so the way you have to think about this is like this. Here's an example. Think of a system that only has conjunction elimination in it. Right? That's sound all right, but it's not complete. I'm sorry about the number 2 here. That'll, it just has to do with the way the animations work. All right, but you'll see why that's there. Okay, so that would be a sound system, all right, but it wouldn't be complete. All right, you just wouldn't have enough rules to do things, and so it wouldn't be complete. So you can have soundness without completeness. You can also have completeness without soundness. Yeah, this is right. So suppose, I gave you a system that has all the rules that we've been using, plus another one that would permit you to affirm the consequent, which is a fallacy, by the way. This is a fallacy. You can't do this. This is really dumb. Right, and suppose I called it arrow elimination 2. That's why I put the number 2 there, okay, so you can see what's going on. That would be a system where you could derive all the valid arguments, but then some invalid ones in addition to all the valid ones. All right, so that would be complete, but it would not be sound. All right, so on the final and on your homework, what you're going to be doing is evaluating claims about soundness and completeness to determine whether they're true or false. All right, so they can be tricky. All right, and they're designed to trick you. All right, but we'll just kind of walk through these to kind of give you an example here. Right, in a sound logical system, there can be derivations that do not correspond to any valid argument. Well, that's false, right? Because soundness just means that every derivation does correspond to a valid argument, all right? All right, number 2, a sound logical system could contain logical truths that cannot be derived. Now remember, logical truths are those things, okay, that, they involve no premises. Right, so in order to derive them, you have to use rules that make assumptions. Well, suppose, and you might like this, suppose I gave you a system where I didn't allow you to use error introduction and negation introduction, but I gave you all the other rules, all the direct rules of inference. Okay, that one could be sound, all right, but you would not be able to derive the logical truth. So that's true. Right? The problem there with that language is that it's incomplete, but it's sound, all right. All right, number 3. In a complete logical system, some derivations might not correspond to valid arguments. Right? Yes, right? Suppose I gave you the system with arrow elimination 2, and then all the other rules that I gave you. Okay, you could derive all the valid arguments, and then some ones that were not valid. That's true. Okay? Number 4, in a sound logical system, every logical truth must be derivable. No, right? And basically for the same reasons I gave you in number 2, all right? You can have, a sound system that just has conjunction elimination, but you're not going to be able to derive logical truths with that system, okay? In a sound logical system, every derivation of a sentence from no premises corresponds to a theorem. That's a logical truth, by the way. A theorem is a logical truth. This is true. Okay, in a sound system, every derivation of a sentence from no premises does correspond to a theorem. Yes. All right, yes. Okay, if it wasn't sound, then you wouldn't be able to get logical truth. Okay. All right, let's talk about number 6 here. And what we have is a complete system. In a complete system, some derivations might not correspond to valid arguments. Yeah, that's right. Suppose I gave you the system with all the rules that we studied and arrow elimination 2. Right? So that's going to be true. You would be able to derive all the valid ones and some invalid ones. All right, number 7, in a sound logical system, it is possible for there to be no derivation of theorems. Again, that's true. Suppose I only gave you the system with conjunction elimination. In a sound and complete logical system, every theorem has exactly one derivation. Well, of course not, right? You can have multiple ones, right? You can have multiple ones. There's no problem with that. I mean, think of the FA arrow FA. Suppose you repeated FA a couple of times just for the hell of it. Okay, you're going to have the same logical truth in the last line. It's just going to be one's going to be shorter and the other one's going to be longer. Okay. Okay, complete logical systems can permit one to derive a contradiction of as a theorem. This one's tricky. But think about it. Completeness, all that guarantees is that all the valid arguments can be derived. It doesn't mean that they're all sound. So you could derive a contradiction as a theorem with a complete system. I don't know what that system would be like. It would be pretty dumb, but you could do it, right? You would have all the rules that I gave you, that I taught you, and then some wacky rules that will allow you to derive a contradiction as a theorem, all right? Okay, number 10, a sound logical system. Sound logical systems have derivations that represent every valid argument. Sound logical systems have derivations that represent every valid argument. No, that is not true, because a sound logical system can be just a system where you have conjunction elimination and that's it. Well, you're not going to be able to represent every valid argument, right? A complete one, completeness is going to guarantee that. All right, so study these, just to kind of make sure you kind of go over these and understand what they mean, right? Because there's just some tricky questions on the homework and on the final about this stuff. All right, there'll be true, false questions like this. So if you have questions about this, just shoot me an email and talk to me on Hangouts or whatever, and I will talk to you later.